All right, let's go ahead and quickly discuss the topics of light and sound. Now, this is a part of the Cambridge IGCSE book. It's a really simple, couple of simple stuff that you need to know in the grade 7, grade A level science. So, what exactly is light? Well, light is simply a form of energy, guys. And this form of energy, it's something that enables us to see around. Of course, that's something we all know, but just think of it as a form of energy that enables you to see. So it's a form of energy that enables us to see. It's important to understand, since we're going into a chapter that's talking about waves and energy in a bigger picture, you know what type of wave light is. Light is considered to be an electromagnetic wave. Of course, later you will learn that it's not necessarily a wave, but you're at the grade 7 level, so let's just keep it simple. Now, it's a part of the electromagnetic wave, and it's got a tremendously high speed, somewhere around 300 millions meter per second. That's fascinating. The speed of light is much faster than the speed of sound, which travels at a mere speed of somewhere around 330 meters per second in air. And then, of course, the temperature is also important, but in air, the usual speed of light, sound is 330 meters per second, and it tends to get faster as it goes through things like solids. And later when we talk about why or how sounds kind of travel, you'll understand why it's faster in solids rather than in air, which is the exact opposite of light, because light actually travels faster in air or a vacuum such as space. And that's because light doesn't actually need particles to get transferred. It's got this mysterious energy in the form of electromagnetic waves, which allows it to transfer all the way from the space where there are no particles to the earth, where there are obviously particles. But that's not the same case for sound, because sound is actually a mechanical wave. And mechanical waves do need particles to get transferred. There are other examples of them. For example, the waves you see in the ocean are considered to be mechanical waves, or earthquake waves are also considered to be mechanical. Electromagnetic waves, on the other hand, one of the parts that are visible to our eye is light itself. There are other types of electromagnetic waves, such as X-rays, infrared waves, but these are extensions of the chapter, so we're not going to get into them. At the same time, you need to also understand that light is considered to be a transverse wave, and that's because the way it travels is perpendicular to the direction of its motion. So if you were to kind of graph a light wave, it would look something like this. You will see a lot of these graphs as we talk about sound and light waves. The top of these graphs are called the crest. The bottom parts are called the trough. If you were to continue this graph just slightly, so you have another crest, the distance between two crests would be considered a wavelength. And a wavelength is measured in meters, and it has a symbol of lambda, which is shown like this. At the same time, the distance between no excitation, or the minimum excitation I'm talking about here, where the graph is on like 0 to its top part to the crest, is called its amplitude. So you can actually calculate the amplitude of a wave simply by looking at how high the crest is. What's the height of the crest, or what's the depth of the trough? Let's go ahead now. There's a couple of things you need to understand and remember, and that's, for example, that lightning travels faster than light. I mean, you see lightning before you kind of hear the thunder. When it's raining and it's really like these big clouds out there, light can be seen first from a lightning strike. Can be seen first. And why is that? Well, you know it. The reason is, obviously, light travels at a much greater speed, about 300 million meters per second, whereas, sound travels at 330 meters per second in air. So that's actually quite a low speed compared to light. Now, when it comes to different types of objects, whether they can create their own light or whether they are consumers of light in some ways, we can divide objects into two categories. Objects are either luminous or illuminous or illuminated or just non-luminous. And you can think about it, luminous is kind of a Latin word, and there's this Latin root there that stands for light. So luminous objects are objects that give off their own light, objects that produce or give off their own light. And there are many examples of luminous objects. One main example is the sun, the stars, a TV screen, a computer screen, so on and so forth. But objects that do not give off their own light are considered to be non-luminous. And examples of non-luminous objects are things like, let's say, for example, a table. A table does not create its own light unless you have light fitted into it. The moon, it's actually a reflector of light from the sun. And planets are also considered to be non-luminous. A very important rule about light is something that is sort of a fancy word, and it stands for rectilinear propagation. Rectilinear propagation is a rule that states that light can only travel in straight lines. So light can only travel in straight lines. This is proven by shadows. If light did in fact, bend around the corners, shadows would not be created. So light is in fact traveling in straight lines. That's why a shadow of the object is usually cast behind if there's a screen or if there's a wall behind of that object. And also if you're riding a car, usually, the light from the car barely passes through the corners. As soon as you get close to the corner, only then you might see some kind of diffraction of the light going into like the alley or the street that you're passing by. So light can only travel in straight line, proven by shadows. Now that we're on the topic of shadows, there's three things we need to know about, three types of objects. Objects in terms of light are either opaque, transparent, or translucent. So what exactly is an opaque object? Imagine you have a sort of a wall that's a brick wall where every single crevice is, sort of filled in with the bricks or some sort of a cement that does not allow even a wrinkle of light to pass through. So, that's considered to be an opaque object because no light can pass through. So opaque objects are objects that do not allow light to pass through. So no light passes through. For example, a brick wall or maybe a wooden wall, anything that does not allow light to pass through. Transparent is anything that is unlike that, like a window that does actually allow light to pass through. The windows at your house are transparent. So something that allows light to pass through. It allows light to pass through. Translucent objects, on the other hand, are objects that barely allow some light to pass through. So imagine you have a window, and this window is either tinted or it's kind of fogged up because of the fact that the weather is foggy, it's really cold, or it's rainy outside. This usually happens, and your car has this system you got to turn on to get rid of the fog on the windows. But basically, translucent objects allow some light to pass through. Some light to pass through. For example, a foggy window, a tinted window. Let's go ahead now. Last but not least, there's two main types of shadows that we discuss at the IGCSE level in grade 7, and those are penumbra and umbra shadows. So imagine you have a very small source of light. This is a small source of light. And next you have a ball or an object. And then behind this ball you have a screen, which is like a window. I mean, sort of not like a window, but actually kind of like a mirror. What happens is the light from the bulb is going to pass around this object and kind of go around its corners. And then there's going to be an image produced on the screen. The image that's going to be produced on the screen, if the ball is sort of close to the small bulb and not that far away from the screen, is going to be an image that is going to be of a shadow. So it's going to be a very clear and dark shadow that is going to be produced in the center, and we call this an umbra shadow. An umber shadow is a very clear and dark shadow that is created when the light source that is using is small, and basically the light goes around the edges and produces this type of shadow. However, if you use a larger light source, there's usually going to be this hue that is produced around this sort of object. There's kind of like a gray hue per se that goes around the main shadow, and we call this part of the shadow the penumbra shadow. You can actually see this on any type of shadow. As you're walking the street, if there's a shadow of you next to you, or maybe on the street, you will find this gray hue around the main shadow, and it's called the penumbra shadow, which is actually less dark. It's actually kind of fuzzy and gray, and so it's going to be formed around the umber shadow. So far we learned that light is a part of the electromagnetic spectrum, and that it's much faster than sound. Let's go ahead now, take a look at the next thing you need to know about light, that is reflection. So what exactly is reflection? Now, reflection is simply explained when you consider a mirror. Imagine you have this mirror over here. According to the law of refraction, if a ray of light hits a very smooth surface like a mirror, it's going to hit that surface and get bounced back. In other words, it's going to get reflected. Now, there's going to be a normal line in the middle here, which is drawn at 90 degrees. It's a line drawn at 90 degrees, and that's the reason for it is mostly for calculations and everything. But for example, let's say this ray of light is hitting the surface at an angle of 30 degrees. Then we can find this other angle here, which is the angle of reflection, is going to be the exact same as the angle of incidence, and that's actually the law of reflection. The law of reflection says that the angle of incidence, or theta I, should be equal to theta r. That is the law of reflection. So this right here also will be 30, and all of them should add up to 90. So this angle here should be 60, and this one should also be 60, as they should add up on each side to 90, and overall they add up to 180 degrees. So the angle of incidence is equal to the angle of reflection. This ray right here is called the incident ray. This ray right here is called the reflected ray. This angle here is called the refracted angle, or the angle of refraction. Sorry, not the refracted angle, the angle of reflection. Angle of reflection. And this angle here is called the angle of incidence, which are both equal to each other in reflection. Now, there are two types of surfaces through which reflection can occur. So basically, we have rough surfaces and smooth surfaces, and thus we have rough reflection and diffuse reflection. So reflection is either A, smooth, or B, rough or diffuse. A rough surface is something like imagine a rusty car. It's not going to look very shiny, and the surface is all, not as smooth as a sort of a mirror. So what's going to happen is the rays of light are going to hit different parts and get refracted or reflected at different angles, like this. However, if you have a smooth surface where the object appears to be shiny, all the rays are going to get refracted. I keep saying refracted, that's another property of light, reflected in the same direction. And they're all going to be parallel to each other. So make sure you know that. The next thing you have to know is the properties of an image produced in a mirror. An image produced in a mirror is going to have the following properties. The first thing you have to know is that the image produced in a mirror is laterally inverted, and that means it's back to front. The image produced in a mirror is actually virtual, and that means you cannot produce it in a real another place, or you cannot produce it on a screen. But the image that you have of yourself, for example, a selfie of yourself on the phone, is real, because you can take that image and then maybe connect it to your TV using Bluetooth or maybe HDMI, whatever you have. So the image produced in a mirror is virtual, it's back to front, and another fancy word for it is laterally inverted. And another thing you got to know about it, it's that it's the same shape, size, and color. And that's obvious because the mirror is not going to change the shape, size, or color that you have if it's a, sort of a normal everyday mirror. And as a result, it's considered to be the same shape, size, and color. And of course, it's virtual because you don't really exist behind the mirror. What you see in the mirror is just a reflection of yourself. You can also use periscopes to see around corners, but that's not really that important. Another thing you've got to be very familiarized with in this chapter is calculating the angle of reflection from like the second mirror. So imagine they give you a mirror and these two mirrors are connected at an angle of like 110 degrees. A ray of light hits this mirror, let's say, for example, at an angle of, let's say, for example, 30 degrees. Let's actually change that. Let's just say it's 60 degrees. What's going to happen is this ray of light is presumably going to hit the other mirror, because these are two mirrors connected at 110 degrees, and then get reflected again. So you can calculate the angle of reflection from the second mirror as well. But let's see how. First of all, this angle over here is also going to be 60, which makes this angle 30, because this whole side should add up. Let me use another highlighter. This whole side should add up to, 90 degrees. Remember, the normal line here is at 90 degrees. Now, over here, as you can see, we have a triangle. So the 30 degrees plus the 110 degrees plus this angle and this and this and this should add up to something, right? But the 30 degrees plus the 110 plus that angle should add up to 180. So together, those add up to 140, these two angles. So that means this angle here is 40 degrees because that's what makes a triangle 180 degrees. And again, this 40 degrees should add up to 90. That means this angle here is 50, this one is 50, and this one should be 40. So keep in mind that in the triangle part, the 110 degrees plus that 30 degrees plus another angle should add up to 180. So obviously that other degree or that other angle is 40 degrees. And then you go on and find the rest. Let's go ahead and take a look at the next thing you got to know, which is refraction. So what exactly is refraction? Actually, I kept mentioning it when we were talking about reflection because I kept messing the words up. But basically, refraction is another very important, fascinating property of light. And I'm going to tell it to you in a very simple manner. Imagine we have the following situations. Just consider the two situations here. A ray of light is going from air to water, and then a ray of light is going from water back to air. Maybe someone's holding a flashlight on the water, and then the light goes from water to air. So here we have the normal line here. The red line is the normal line. It's always there at 90 degrees. Imagine a ray of light goes from air to water, and then a ray of light goes from water to air, the opposite way. So what do you think is going to happen? Well, it turns out that water is technically more optically dense than air. Right? Think about it in terms of states of matter. It's a liquid, so it's more dense than the air. The air is less dense than water. And technically, whenever light goes from something that's less dense like air into water, something fascinating happens. And that's the fact that light actually slows down. Because it slows down, it's going to bend towards this normal line. So it's going to bend towards the normal line. Towards the normal line. If the ray of light goes from water to air and it actually is going from something that's more dense like water into air, it's actually going to do the exact opposite and it's going to speed up. And because it speeds up, it's going to run away from the normal line. And as it runs away, the ray of light is going to bend away from the normal line. So the situation is if a ray of light goes from a less dense medium, to a more dense medium, then what's going to happen is the ray of light slows down. So light slows down, and as a result, it bends towards the normal line. If the same ray of light goes from something that is more dense to a medium that is less dense, for example, it goes from glass, Example, it goes from glass, it goes from water, it goes from diamond into air, which is definitely less dense than them. Then what's going to happen is the ray of light is going to speed up. And because it speeds up, it's going to bend away from the normal line. It bends away from the normal line. So basically, the bending of light is considered refraction. Refraction is the bending of light. Simple like that. All right, so that's the whole idea behind refraction. There's another thing you have to understand and remember in refraction, and that's a specific phenomenon that happens only in certain circumstances. So consider the same situation where a ray of light was going from, for example, water into air. In this situation, we have something called the critical angle for every single medium that you have to know in refraction. For example, the critical angle between air and water is roughly around 43 to 49 degrees. So let's say it's around 43 degrees. What's going to happen is if this ray of light was to strike the water at exactly 43 degrees, a phenomenal thing happens. We no longer have refraction, but the ray of light actually gets refracted at 90 degrees. So it's going to go along the boundary like this. We call this the critical angle. So the critical angle is the angle at which the ray of light gets refracted at 90 degrees. So the ray of light gets refracted at 90 degrees. And keep in mind, this only happens if we're going from something more dense to less dense, for example, from water to air. That's very important. Now, let's assume we were to kind of increase the angle just a tiny bit more. What's going to happen next is even more fascinating. So if the ray of light was to hit the boundary at, let's say, 60 degrees, which is, relatively larger than 43 degrees, the ray of light no longer gets refracted, nor refracted at 90 degrees, or going to bend away or towards. In fact, it's going to get reflected back. So the boundary acts just like a mirror. And of course, because of the law of reflection, this angle over here is also going to be 60 degrees. This is known as total internal reflection. And it happens when the angle of incidence here is greater than the critical angle of the substance or medium. So when the angle of incidence is greater than the critical angle, the ray of light gets reflected. Ray of light gets reflected back. And obviously, if the angle of incidence is equal to the critical angle, we have the ray of light getting refracted at 90 degrees. And if it's less than the critical angle, we then have refraction, like the first two examples I told you about. Now, one other very important, use of, for example, total internal reflection in technology is in optic fibers, where, for example, they use to transfer internet and data at really high speeds, as well as endoscopes for the surgeons or people who want to undergo surgery to look at inside their human body rather than opening them up. And then that's a really fascinating feat of technology, because it allows us to look inside of humans without having to kind of, dissect them and open them up per se. Now, that's basically it when it comes down to refraction, reflection, and the properties of light. The next important part you have to learn about is the topic of color. I'm going to quickly go ahead and talk about what color is. Basically, color is divided into seven colors when we pass it through, when we pass white light through a prism. And the seven colors are summarized like this. I'm going to write each color with its own color. So basically, red, and then we have orange. You can memorize it like this. In fact, this is a good way, good mnemonic to memorize it. Red, orange, and then yellow, and then blue, and then, sorry, I messed up one color here. So red, orange, blue, yellow, and green, orange, blue, beige. So weave that stands for basically red, orange, yellow, green, blue, indigo, and violet, which are the 7 colors of, color, and the things that we see in visible light spectrum. If you go towards the left side, this is not necessarily for the guys that are doing normal grade 7 physics, but for people that are above this in A levels or IGCSE. If you go towards the left side, the wavelength of these colors increase, the energy and frequency they have decreases. So red light would have less energy and frequency than, let's say, for example, violet and blue. Whereas if you go towards the right side of the spectrum, the wavelength decreases while the energy and the frequency of these particles is going to get higher. The main thing that we study in colors with regard to light is how the absorption of colors happen. For example, we have to know if a object is white, then it's going to reflect all the colors of white. So white surfaces reflect all colors. And what that does is, if something is going to reflect all white or all the colors, is it's going to absorb less heat. That's why in a lot of countries like Greece or places where there's a lot of sun and that can cause a lot of heat inside the house, the houses are built in white, and even the people dress up in white. Now, if not all the colors are absorbed, an object actually appears to be black. But there's a couple of things you got to know. White, if an object is white and you put any color on that white object, then that color is going to get reflected. So if you put blue on white, the object appears to be blue. If you have another colored object, let's say the color of the object is blue, and you put green color on blue. This is, of course, we're talking about light. We're not talking about paint. A lot of people tend to mistake this. When you put green on another color, or any color on another color, green on blue, yellow on orange, red on blue, you're going to get a dark color. So the object appears to be dark or black. And also at the same time, if you put white color on any object, let's say the object is, for example, blue, and you put white on blue, what's going to happen is the reflection or the color that you see is also going to be blue. So what that means is if you wear, for example, a yellow shirt under white light, the shirt will look white. But if you were wearing the same yellow shirt under, let's say, for example, a blue light, then your shirt would appear to be dark or black. The same thing goes for filters. Imagine we have a filter here that is red, and we pass white color through it, and we also pass red color. What comes out is also fascinating. If you pass red, obviously red on red gives you red. White on red would also give you red color. But what if we pass, for example, green through this red filter? It turns out the color that comes out, like I mentioned, is actually a dark shade or a black color. So these are the things you have to know regarding color. Now, in another video, in part 2 of this video, we're going to be discussing the properties of sound, echo, and potentially gravity in the chapters that you have to know in the Cambridge IGCSE book. Best of luck, do lots of practices,